The first time that we were asked to run a Haas mill with a probing system on it, we asked ourselves the questions: where do all of these probed offset values come from? What do they even mean? And a couple minutes later, we stopped asking questions. We just watched some video that showed us how to probe our tools and our parts, and we moved on because we had parts to make. Well, today we're going to answer those probing questions. We're going to find out what all of our probed offset values actually mean in this Haas tip of the day. In the world of machining, we rely on part drawings. Dimensions on these prints are usually called out from some reference feature, a 0 point that we call a datum. Now, our Haas mills also have a datum, a 0 that all of our offsets are based off of, that we call our home position. Now, contrary to popular belief, our Z home position is not at the edge of our Z travel. When we press the power up key on this Haas mill, the spindle head will travel up and find the edge of our Z travel before moving back down to our tool change position before putting tool 1 in the spindle. Setting 81 defines what tool we want in the spindle after power up. It is this tool change position that our Haas mill uses as our home position, our datum from which all other Z tool and work offsets are referenced from, our machine coordinate system. If you run mills every day, you might have noticed that after turning on the machine and pressing that power up key, the Z home icon is not always displayed. This will happen when the machine has been shut down with tool 1, T1, already in the spindle. No tool change at power up to T1 was needed, so our machine comes to rest at the edge of our Z travel, which we know is not our Z home. In this case, pressing the power up key a second time will move our Z from the edge of travel down to our tool change position, which is our Z home position. Look, home is where we start our day, and a tool starts its day at tool change position. Home is 0. Machine Z0, our tool change position, is our first reference point. Step 1 in understanding where all of our probed offsets, both tool and work, come from. Our second reference point is right here, at the top of our optical tool setter, our OTS. Now, during our probe calibration process, the control figured out the exact distance from our spindle to the top of our OTS stylus and stored it for later reference in macro variable 582. Now, just saying from our spindle is pretty vague, not precise at all. I mean, are we measuring our spindle from here or from here? To solve this problem and to make sure that everyone is on the same page, it was decided many years ago by some clever people behind locked doors that we would take all of our spindle and tool measurements from our spindle gauge line. Now, on this machine with a 40 taper spindle, our gauge line is a theoretical line that intersects our spindle or tool taper at exactly 1.75 inches, 44.45 millimeters in diameter. Now, this is a really difficult position to measure from, an imaginary theoretical line set in between two tapers. This is why most of us just purchase a precision ground calibration tool with a known gauge length etched right onto the side of it. Now, this one is 5.0026 inches, or 127.066 millimeters, from tip to gauge line. This is our gauge length. When we calibrate our OTS, we are using a calibration tool of a known length. Our machine now knows exactly how far it is from the top of our OTS to our spindle gauge line. Gauge length is also how we measure our holders without tools in them. This is an ER25 holder with a 4-inch, about 100 millimeter gauge length. Our tool length offset is the positive length of our tool from the tip of that tool to its gauge line. When a tool is probed, the control takes the current machine Z position, which is our distance from our Z home, and it subtracts the calibrated location of the OTS stylus, which is stored in variable 582. It enters this value as our tool length. Now this all works out to the length of a tool from gauge line to tip. Now the height of our OTS is not critical. We can use any spacer underneath it as long as we recalibrate to let the control know where the top of our OTS stylus is, compared to machine Z home. It is possible for us to create our own calibration tool by measuring from the spindle face to the tip of a pin in a holder, and using this estimated value when we calibrate. This is fine. Our probe won't be calibrated to some industry standard gauge line, but we can still probe and make parts on that machine. Now, I like to compare this to tuning a guitar by ear. I can tune this guitar to itself, and it will sound fine if played only by itself. But if we want to play along with others, every instrument must be tuned to the same standard, to the same tuning fork. A qualified calibration tool is like a tuning fork that can be used on any of our machines with the same spindle taper, like any of our VF mills or our UMC, and even our offline tool presetters. They can all be kept in tune with each other if we use a calibration tool. By using a single standard to calibrate all of our machines, we can carry a tool along with its offset from machine to machine, getting the same length offset regardless of which machine or presetter the tool was originally probed on. Tip to gauge line, that's our number. Now this is really useful if we are trying to save setup time by pre-staging entire jobs. Back on our control position screen, our machine coordinate system, or MCS, is just labeled as machine. Our X and Y zeros are the edges of our XY travel, while our machine Z0 is our Z-axis tool change position, Z0. Now our tool length offsets, TLO, are the distance from our tool tip to our tool's gauge line. This is a 40 taper machine, so our gauge line is at 1.75 inch, 44.45 millimeters in diameter. For a 50 taper tool, it is at 2.75 inches, or 69.85 millimeters. And on a 30 taper machine, our gauge line is at 1.25 inches, or 31.75 millimeter gauge diameter. Now, once we understand our machine coordinate system and the whole concept of gauge lines, moving on to setting our work coordinate system, our WCS, is an easy lift. This guy right here is our work probe. It's our optical machine probe, or OMP. We will use this spindle probe to set our work offsets, to let the control know just how far our work zero is from our machine zero, how far our WCS is from our MCS. We have a tool offset page to let the control know just how long each tool is. And we have a work offset page to let the control know how far our part is from our machine zero. When we calibrated our spindle probe, its length offset was recorded just like any other tool. So the control knows exactly how far it is from the tip of our probe to our spindle gauge line at any time. When we probe the Z-axis top of our part, the control will take this machine position as the spindle probe is triggered and subtract the tool length offset of our work probe and use this new value as our G54 work offset Z value. Machine Z position minus our probe length offset. Now with that probe length removed from the equation, it means that our work Z0 is really just the machine position where our spindle gauge line meets our part. Now, I don't want to break anything, so we have swapped out our steel for a chunk of foam, and we're going to jog down our spindle until our spindle gauge line reaches the top of our part, our WCS Z0. And check this out. On the work offset page, we can see that our current machine Z position exactly matches our probed G54 Z work offset. In fact, if we commanded our spindle to G54Z0 using no tool offset, this is where it would go. And if we add in a tool, along with the code to call that tool's length offset, it would put the tip of our tool right at our part Z0. When machining a part, the control adds each tool length offset to our active work offset, giving us precise and adjustable tool and work positions. Having a general idea, this theory of where all of our tool and work offsets come from, can have some real useful benefits. In fact, we can often tell if an offset mistake has been made just by glancing at them. Tool offsets on machines with probes have positive length values. If a tool were set manually using paper or some kind of height setter on a machine without a probing system, it would nearly always have a large negative value for a tool length offset. If we ever come across a tool offset page that shows both positive and negative tool length offsets, something has gone terribly wrong. We should take this as a warning sign. Some things should never be mixed. Things like, yes, nuts and gum, sure, and positive and negative tool length offsets. Just recognizing the difference between our machine Z0 and the machine Z edge of travel is going to help us program our machines in different ways. When we command our spindle to home with a G53 G90Z0 or a G28 G91Z0, we are not sending the spindle to the edge of travel. We are sending it to the tool change position. And this position is different on machines with umbrella tool changers. These machines will often have 4 inches or 100 millimeters of Z travel above our Z0 home position, where mills with side mount tool changers may have less than an inch. Now, there is no difference in overall travel between a machine with an umbrella tool changer and one with a side mount tool changer, but that travel is centered differently because of the different tool change positions. Our VF4 here has 635 millimeters, 25 inches of usable Z travel, regardless of the tool changer that we put on it. This has been the theory behind probed tool and work offsets. Now, if you want practical examples of how to actually probe a tool or probe a part, we've made videos on that. Check out the link in the description. And if you don't have a probing system on your Haas machine, that's okay too. We've got videos showing you how to set all of your offsets manually. Check out the links. Well, thank you for letting us be a part of your success and for watching this Haas Tip of the Day.